Hey there, welcome to Rationality, Reason, and Reality. I'm Supernova. In the last video, I went over some myths that people hold about infinite numbers and math in general. And today, as promised, I'm going to go over how to use inductive logic to be able to do the regular sorts of math that we do with finite numbers, but apply them instead to infinitely long numbers. And to start with, I'm going to show you an example of an argument that people make to prove that 0.9 repeating equals 1. Here it is, right here in all its glory. In the first line we have 1/3 equals 0.3 repeating. And then we multiply both sides by 3. And we get 1 equals 0.9 repeating. That seems pretty airtight, right? I'm kind of curious. How did we get from there to there? Now, I've done some math videos in the past, and what I told my viewers to do was just pretend like the infinitely long number had a final digit and do the math as if that was the case. And a lot of people complained and said you can't do multiplication with an infinitely long number because there is no last digit, there's nowhere to start, and so you can't finish. And yet none of those people have ever had a problem with this proof that works in their favor. They just don't like it when I do it. Now, I'm going to show you how to skip that entirely. You don't actually have to multiply an infinite sum. You're going to use logic to figure out what it would be. To use inductive logic, we want a few data points that form a pattern, and we assume that that pattern continues based on those data points, and so we make a general rule out of it. For instance, you know that if you multiply 0.3 by 3, you get 0.9. If you multiply 0.33 by 3, you get 0.99. If you multiply 0.333 by 3, you get 0.99. None of this should be surprising, and of course, you don't actually have to do any of this on paper. Very easy math. You know that if you multiply a string of 3s after the decimal point by a 3, you're going to have a string of 9s after the decimal point. That is as long as your string of 3s was. So there's no reason to believe otherwise. When you multiply a string of infinite 3s, it's not going to break this rule. You're going to have a string of infinite 9s. And mathematicians agree with me on this. I'm not saying anything controversial here. I know how to do this math. Maybe a lot of people just kind of figure it out by intuition, or maybe they're working from the left rather than the right. I don't know how most people do this, but I know how I come to it. I'm building a pattern from what smaller finite numbers demonstrate, and then I use that on infinitely long numbers. And I find the pattern should hold. Now, when we use inductive logic, we don't have things such as true and false conclusions. We have weak and strong inductive arguments. And how strong an argument is based on how many data points fit that pattern without any counterexamples. And there are literally an infinite number of examples that we have that all fit this pattern. It is as strong as an inductive argument gets. This is very solid inductive logic. And so this should work. Now, here's where I get into the territory where people are going to disagree. What if we took a number like 0.4 repeating and multiply it by 3? That's a little trickier because the outcome isn't going to be what most would consider a real number. It's going to be something that's hedgy and just doesn't feel right. But let's use this same method consistently, because that's what rational, logical people do. Use the same method and not make arguments of special pleading or say no, this one doesn't fit when we do it the exact same way. Let's do it. If you multiply 0.4 by 3, you get 1.2. If you multiply 0.44 by 3, you get 1.32. If you multiply 0.444 by 3, you get 1.332. And you'll find that if you do this with longer and longer strings of 0.4, you will get a longer and longer string of 1 point string of 3s 2, And the number of 3's will be as many 4's as you had in the original multiplication problem minus 1. And this works in every case from 1, 4 to infinite 4's, one should think. So what would we have if we multiplied 0.4 repeating by 3? Well, we would have 1.3 repeating 2. Now this is the problem, that final 2. When people think of infinity, they don't think that it has an end, because technically infinity means never ending. But just because it has an end doesn't mean that it technically has an end as we think of it. It's still infinite in the middle. Now this may be rather strange, but let me give you another example. Consider the real numbers between 0 and 1. Again, mathematicians have no problem with understanding that this is an infinite set. There are infinite numbers between 0 and 1. Well, what if you were to list them all in order from least to greatest? Well, your list would start with 0 and end with 1, but you would have an infinite set of numbers between it. It would be infinite, despite the fact that there is a last number and a first number. And you may think, well, this isn't a true analogy because we're talking about a list of numbers rather than a single number. Let's make it into a single number. Let's put a decimal point before it and just take the first digit of all those numbers in that list. We would have 0.0 repeating, 1 repeating, 2 repeating, 3 repeating, all the way to 9 repeating, and then a final 1, because you still have that 1 at the very end. And that doesn't feel like a number that should exist, but nonetheless accept it. It does. It can. There's nothing logically wrong with such a number. So one of the major hang-ups, one of the reasons that mathematicians have gotten this so wrong is because they're not comfortable with these infinite sums that end with a finite digit. But that's just the way it works. I'm sorry, accept it. You can argue in the comments all you want with me, but I'm acting consistently. I'm using the math the same way on every number. There's no counterexample that I know of where I get different totals using this method. So we've done this with 0.3 repeating, 0.4 repeating. Now let's get to the heart of the matter. How does this demonstrate that 0.9 repeating doesn't equal 1? Well, because 0.9 repeating doesn't have the properties of 1. If you subtract 0.9 repeating from 1, you don't get 0. If they were equal, they should equal 0. Everybody agrees with that. Again, this is not controversial, and yet it doesn't. Because if you subtract 0.9 from 1, you get 0.1. If you subtract 0.99 from 1, you get 0.01. 0.999 from 1, you get 0.001. And you see that this pattern continues until you're subtracting an infinite number of 9's from 1. You have 0.0 repeating 1, which is what intuitively you would think it would be if you weren't listening to expert mathematicians. This is what it feels like it should be, and logically that's what it is. Now try it the other way around, because again, if 0.9 repeating and 1 are equal, there shouldn't be any problem with subtracting the other one from. So 0.9 repeating minus 1, what does that look like? Well, it doesn't work. We can't subtract larger numbers from smaller numbers. And I would love to see somebody try it. You can't even do this inductively, because you can't subtract larger numbers from smaller numbers. You have to reverse them and then give it a negative sign in the front. How about 0.9 repeating squared? If 0.9 repeating equals 1, then the product of that should be 0.9 repeating or 1. Either one would be an acceptable answer, because if you got 0.9 repeating, it would be as if you had multiplied it by 1. Or, of course, if you got 1, that is the product of 1 squared. And what do you get? Neither of those things. 0.9 squared is 0.81. 0.99 squared is 9801. 0.999 squared is 0.998001. And again, there are an infinite number of finite numbers that you can do this with, and you'll always find the same pattern. You'll have an 8 just before the middle and a 1 at the end, and between them a number of zeros equal to the number of 9s that you started with minus 1. And at the beginning you'll have a number of 9s equal to the number that you started with minus 1. And this pattern continues. So if you were to square 0.9 repeating, you would get 0.9 repeating 8, 0.0 repeating 1. That is not 0.9 repeating, that is not 1, and it's not a number that mathematicians like, but deal with it. This is how it works out, and this is how we should expect it to work out if 0.9 repeating did not equal 1. I know the burden of proof is on the mathematicians, and they believe that they've met it by showing all these proofs, and I am going to go over the rest of these proofs, including this one that I demonstrated at the beginning, and show why they don't work. Because once those have been presented, yes, the burden of proof is on me to disprove them. But nonetheless, if you believe 0.9 repeating equals 1, you ought to be able to demonstrate that 0.9 repeating has the properties of 1. Nobody ever takes time to actually try to prove that. And when you do, you find that it doesn't work. Mathematicians will make an excuse because they don't have the tools to do such multiplication. But anyway, I hope I've given you enough food for thought in this video. In the next one, I will tackle the example that I gave you, plus 1 or 2 more, and from there on I am going to attack many of these arguments that mathematicians have proposed prove that 0.9 repeating equals 1, but don't. And a lot of them we don't even have to do inductive math to prove that the logic is just bad. A lot of them are just rounding errors. But anyway, I'm glad you watched this video, and I hope you enjoyed it, and I hope it gave you something to think about. I hope I convinced you, and I hope you'll return for the next one. Peace out.